Okay, we're recording. Thank you. What are we talking about? What are we doing? Okay, so before we get into curve sketching from a calculus perspective, it's kind of funny because I'm doing curve sketching polynomials in pre-calc right now, and I'm like, remember this, like you guys would identify the zeros, the multiplicity of the zeros, you'd plot the points, you figured out the end behavior, and I was like, don't worry about what's happening in between the zeros, right? Like how high up the graph goes or how low it goes. You need calculus to do that. Guess what? We're here. Yay. We're figuring that out, okay? So that kind of goes back. In pre-calc, we filled our functions toolbox with ways to identify different characteristics about a function that could be useful in applications. And now we're going to do that, but using calculus. Okay, so we're going to start with examining where there are high and low points in the graph of a function. We're going to first start with like the very highest point or the very lowest points on our graph, which would also be helpful for determining the range of a function. Remember how like previously we've been like, we have to look at what the graph is, or I guess you could know end behavior, but if like you're dealing with a polynomial, let's say where both ends point up, you're like, well, I know the range goes to infinity, but I don't know what the starting point is, right? But now you will. Now you have those tools, which is awesome. Okay, so our definition of extrema, let f be defined on an interval I containing c. F of c is the minimum of f, so the smallest function value of f on an interval if f of c is less than or equal to all the other function values on the interval. Does that make sense? Like a function value will be the minimum function value if it's less than or equal to all the other function values, okay? And a function value will be a maximum, like will be the largest function value if it's greater than or equal to all the other function values on an interval. And I'm not specifying what kind of interval yet. We're just thinking about an interval of numbers. Could be all real numbers, could be closed interval, half open interval, just on an interval. Is everyone with me to here? Okay. No? So that first statement, f of c is a minimum. So a function value, a y value, would be the smallest y value if it's less than or equal to all the other y values of the function on an interval.
So it's going to be the least if it's less than all the other ones.
Yeah. And the most, it's kind of well done, right?
Yeah.
And will be a maximum if the y value, the function value, is greater than or equal to all the other function values. Cool? Okay. So the minimum and maximum of a function on an interval are extreme values, or extrema. The singular form of extrema is extremum, and I screw this up constantly, so I apologize in advance for using the correct one, okay? Of a function on an interval. So the minimum and the maximum value of a function on an interval are also called, depending on what textbook you're in, and you need to be comfortable with both sets of terminology, so are either called absolute minimum and absolute maximum, or the global minimum and global maximum, and you need to be comfortable with both. Okay, so absolute and global mean the same thing. Are you typing what I'm saying?
Oh, yeah.
Oh, yeah. In LaTeX? Are you in LaTeX?
Yep.
Wow.
Did you do this in LaTeX?
No. I use Spider software. I tried to learn LaTeX in college, and I was like, it was taking me way too long to get through papers, but they look so pretty.
I know.
Okay. Love that. What are we talking about? So absolute and global mean the same thing. So referring to an absolute minimum or global minimum means like the very smallest function value, okay? Absolute maximum or global maximum refers to the very largest function value. Right, Billy?
Yes.
So let's do a little exploration, and you can do this with somebody next to you if you'd like, but and it seems like maybe Billy's already started this, but why don't you go through and sketch each of these graphs on the given interval, and then identify the extreme values and where they occur. So the extreme value would be the function value, like the absolute maximum or absolute minimum would be the function value, and then the ordered pair that describes the point would describe the location. So sketch each of those functions. I'm going to kind of work through them too.
Is there a typo for you? What even is that?
Negative
Where?
3, and negative 3, 1.
No, type it on both of them. Or not type it, graph on both of them. Consider on both of those intervals. So draw two different graphs. Not a typo. Well, but one is including endpoints,
Yeah,
one is not. How's it going, you guys?
Yes, Billy, it's raining.
It was raining.
Yeah, it was raining.
So it's like,
It's because we were supposed to have Veterans Day off.
I was so lucky. I was sitting outside the whole time.
It's gonna strike lightning.
I was like, hopefully she's watch it actually strike lightning.
Okay, you guys, have you gone through and sketched?
Almost.
And then you should also be identifying what the extreme values are and where they occur on each of those graphs. Then we're going to go through it together and check in.
It's crazy. A torrent of rain. Can I just go like see it?
Classic rain.
It's coming down. Wow, it's sideways.
Yeah.
Wait,
Slanted. Slanted. We got slanted rain.
It's time to get out on the road.
It was a lot of water.
Hydroplane.
Guys, you do
Oh my God.
Oh,
That
I'm
was
sorry,
so
Zach.
funny.
You're-
It was hot last week.
Oh my.
Oh, wow.
My car's gonna be
Okay,
covered
right there.
in
You
weeds.
gotta get.
I think
I believe the plan has to do
I
the
think
rain.
that we should, that like we said better do it.
That isn't so
We're
clean.
sure have better than
Imagine
It's so exciting.
being able to.
Rain.
No, you imagine you went to bar, but there's no freeway.
Wow, that's a lot of rain. Oh yeah, that's awful.
All right, you guys.
Imagine you guys
If you
have
really
to
set
walk.
it.
No. Yeah.
Awesome.
I live close to the bay.
So let's get started.
There's no freeway.
What color do I want to use? We'll use red. So first of all, for f of x equals to 2x plus 5, this linear function on the closed interval from -1 to 3, what is the minimum value of the function?
It might be -1.
What's the minimum function value? 3. 3 would be the minimum value. We would say the min is equal to 3. It occurs at the point -1, 3. But the minimum is 3. What is the maximum function value? 11. And it occurs at 311. So the maximum value is 11, and it occurs at 3, 11. So the point describes the location but the actual extreme value, the actual maximum value is 11. Okay. And we all see that. We all agree? All right, B, let's look at the first one. So x squared on the closed interval from -3 to 1. On the closed interval from -3 to 1, what would the minimum value be? 0.
Oh, 0. Okay.
0. And that minimum value of 0 occurs at the point 0, 0.
Is it just min equals 0, or like is it like minimum is y equals 0? Or?
We'll get into that. For now, you can just write it how I am. We're just identifying maximums and minimums without getting into the nitty-gritty, like what type of minimum or maximum is this? For now, we are just talking absolute max and mins, global max and min. So we'll just call, and anytime you're asked for a maximum or a minimum, it refers to global or absolute. Okay, what about the maximum?
9.
9. So the max is 9. And it occurs at the point -3, 9. Yup. Okay. What about on the open interval from -3 to 1? What's the minimum?
0.
Still 0. Still 0. And occurs at 0, 0. What about the maximum?
8.999.
9's not a point on the graph on the interval from -3 to 1. Can we with confidence say what the maximum value of the function would be on that interval?
No.
There is no maximum. No maximum. Because you could be like, oh, 8.9999. And I'm like, well, what about 8.999999?
What if you took the limit?
But the limit isn't the function value. When we're talking about good idea, but when we're talking about maximums and minimums, we're talking about like the actual function values. Okay? So there is actually no maximum on the open interval from -3 to 1 for x squared. I know, weird and uncomfortable. A little bit uncomfortable, right? Because you're like, I see it. I see where the maximum is. But like you can't, it's kind of like with limits. Like you can't actually say what it would be. Okay. 2 sine x. On the closed interval from 0 to 2 pi, where's our minimum? Or what's our minimum?
3 pi over 2.
No, what is our minimum?
-2.
-2. -2 is our min. And then, like Arnav said, it occurs at 3 pi over 2, comma, -2. And then the maximum is +2 and occurs at pi over 2, comma 2. That one's kind of pretty straightforward. A little less straightforward. What do we think? What's the minimum? 3. What's the maximum? They're both 3 is the min and the max.
And then what point would we go? Just like
All those points. All of them between -2 and 2.
So minimum and maximum exists even if like all the y values.
Well, it's great. If you go back up, good question. If you go back up to our definition, right?
All
It's if f of c is less than or equal to all the other function values, or if f of c is greater than or equal to. Which again, I know some of these make my eye twitch, and I'm like, but yeah. Going back to the definition, both the minimum and maximum values would be 3. Piecewise. What do you think for min? 1?
Comma 1.
Well, the min is 1.
And it's located.
It's located. There's a difference there, right?
Yeah.
1 comma 1 describes the location. What about the maximum?
There is no maximum.
There is no maximum. No max. No max on the closed interval from 1 to 4. Okay. I want you to look at all of those graphs. And why don't we do grouping, grouping, grouping. Talk about those graphs. What can you say about a function f that is continuous on some closed interval with regard to extreme values? What do you notice looking at those graphs about a function that is continuous on some closed interval? I would maybe identify all of those graphs that are continuous on a closed interval and see what you can conclude about them. So go back and look at those graphs. Talk to your groupings. Face each other. Turn to face each other.
So there's going to be a maximum always. Yeah.
You can maybe make a note. I'm going to fill those lines in with you guys, but talk to your groups about what you think you can conclude.
What did you say about a function that's continuous? There's always going to be a minimum and a maximum.
Yeah.
Might be the other way around.
Wait, Mr. said, like, our closed interval is the one with the brackets, right?
That include the endpoints.
Continuous and closed.
Did you talk to your group? Did you guys talk to each other? Did you come up with a statement you could make?
Yeah. Yes.
And you all agree on it?
Yes.
Okay. So first of all, you guys, why don't we identify which of these graphs are continuous on a closed interval? Is A continuous on a closed interval?
Yes.
Yeah. Okay. What about our first graph on the interval from -3 to 1 with the brackets?
Yes.
Continuous on closed interval? Yeah. What about with the parentheses?
No.
Continuous, but not closed interval, right?
Yeah.
So we're not going to highlight that one. What about 2 sine of x on the interval from 0 to 2 pi? Continuous on a closed interval. Okay. 3, f of x equals to 3 from -2 to 2. Yup. And then what about piecewise from 1 to 4?
It ain't continuous.
Not continuous, right? There's what type of discontinuity occurs?
Removable.
A non-removable discontinuity at 3, so we cannot highlight that one. F of x is discontinuous on the closed. We have the closed interval, but we don't have that it's continuous. Okay, so looking at those 4 graphs, what do we notice about all 4 in terms of extreme values? There's both a minimum and a maximum. So if we can conclude that if a function is continuous on a closed interval, the function will have both a maximum and a minimum.
Just above, didn't you say there's no maximum? The last problem?
It's not continuous though.
Okay.
It has to be
So if it's
continuous on a closed interval, yeah. So functions that are continuous on a closed interval have both an absolute or global minimum and an absolute or global maximum on that interval. Okay, so this can also be referred to as global, right? Depending on what textbook you're in. I think of what the AP is. I feel like I've seen both. Like you should be familiar with both. They use global. Nope, they also use absolute. They use both. So functions that are continuous on a closed interval have both an absolute minimum and an absolute maximum on that interval. This is known as the extreme value theorem. Okay, the extreme value theorem you do need to know by name. Okay, know by name. And the conditions for it to apply. Extreme value theorem is what type of theorem? We've talked about this type of theorem previously. Does it tell you where to find the extreme values?
No.
No.
It says existing theorem?
It's an existence theorem, exactly. So you know if those conditions apply, the function is continuous on a closed interval, that there will exist an absolute maximum and an absolute minimum on that interval. Doesn't tell you where, but it does tell you that both exist, and you know to look for them. Any questions up to here? Are we following along okay? Okay. So extreme values of a function can be relative rather than absolute. So suppose f is a function defined on the closed interval from a to b as shown below. You guys get my little hand-drawn function. Okay. The value of f at c is a relative maximum. So this point right here, c comma f of c is the location of a local maximum or relative maximum. Because there is an open interval containing c on which f of c is a maximum, since there is no larger value of the function in the locality of c, like in the neighborhood of c, f of c can also be referred to as a local maximum. So relative and local mean the same thing, in the same way that absolute and global mean the same thing, okay? And we need to be comfortable with both sets of terminology. So going back here, so c comma f of c is the location of a local maximum, meaning we can say that f of c is a local or relative maximum. I wrote that L weird. Okay, before I go on to the next part. So like if we were to zoom in into the neighborhood of C comma F of C, do you see how this is the highest point in that neighborhood? So that's why we're like, oh, there's a relative or a local maximum that occurs at that point. It's the highest point in that, like you can create an open interval around that point and it would be the highest point with the largest function value. Good? Do you recognize that the endpoints of a closed interval can never qualify as relative extrema? Label the remaining relative and absolute extrema on the graph of f. What do you notice about the value of the derivative, f prime, at each of the relative extrema? So before I have you do that, notice, like if we consider an endpoint here, what's the issue with the endpoint being a local max or min? You don't know there's nothing to the left. You can't create an open interval around the point. So for something to be a relative or a local max or min, you have to be able to create an open interval around it. So I want you, in the groups that you're sitting in, can you please go through and label the remaining relative and absolute extrema? So you're identifying the absolute max and mins. This is a continuous function on a closed interval, so you know both exist. And also labeling the other relative or local max and mins. Take a moment to do that with your groups. Talk to each other.
This would also be, relative.
Yeah, that would also be.
So f of a is
I guess I'm just saying, if it's a total max, the slope is undefined.
F of A
She's absolutely, you notice that? So it's like, this one is a middle term, right?
Yeah, but like if you have a follow nodal, then like the slope at like any local place could be like 0, right? Because like it just increases all percent then like, or it could just be equal and then just stop by from 0 to 0.
Yeah, so the point is the local ones are 0
You don't
and
know what's around.
absolute is undefined.
No, the absolute, I feel like the absolute one is just like, it could be any of the local ones, but it doesn't necessarily have to be undefined.
Yeah, I guess so.
local max.
Wait, is that like, yeah, what's it?
It was a attempt at myself out.
How are we doing, you guys? Good. Have we labeled our other local and global max and mins? Okay. So tell me, are there any other relative maximums? Or actually, how about this? Let's do the absolute first. Because this is a continuous function on a closed interval. What is the absolute minimum of the function on this interval?
F of A?
F of A?
Yeah.
Yes. F of A would be an absolute minimum. Or global min. My Apple Pencil is really glitchy right now. F of A would not be a relative max or min, and that's because that point is not on an open interval. It's at the end point of the interval. What about the absolute maximum of f of x on this interval?
F of e
f of e. Okay, so f of e is an absolute or global max. Okay, I agree. Is f of v also a relative
Yeah.
maximum? Yes, it is. Yes, it is. If we zoom in on that point, it's the highest point on that interval. So, and f of e is a relative, or local max. Good. Are there any other relative maximums? What about relative minimums? F of D. F of D would be a relative minimum. Okay, if we were to zoom in on the graph there, f of d would be the smallest function value on that open interval. Okay, so we have these points. We've identified local and global max and mins for the function f. On the closed interval from a to b. Now the other part of the question, what do you notice about the value of the derivative at each of the relative extrema? What do we notice about f prime?
They're horizontal last two.
They're either undefined or they are.
Okay, I think you guys are saying the same thing.
Yeah.
You're talking about the graph of f prime.
The derivative of the points.
The derivative of f would either be
0 or undefined.
0 or undefined, okay? So notice at f of c, or at c comma f of c, there would be a, oops, that's not what I want. There would be a horizontal tangent line at c comma f of c, meaning that f prime of c would be equal to 0. Okay. At d comma f of d, what type of tangent line would we say occurs there? Horizontal. So we could again say f prime of d would be equal to 0. Okay. What about at e comma f of e?
Undefined.
Yeah, f prime of e would be undefined because there's no tangent line that could be drawn. That's a sharp corner, or in particular, that's what we call a cusp. But f prime of e would be undefined. Okay. So to summarize here, we could say that f prime of 0, sorry, not f prime of 0, f prime of x is equal to 0, meaning there would be a horizontal tangent line. Or f prime of x is undefined, meaning f is not differentiable at that point. And that would either be because there's a vertical tangent line or no tangent line. And again, this was for the relative extrema. We discovered that f prime, the derivative, would either be equal to 0 or undefined. So we will call the x-coordinate of each of these points a critical number of the function. The definition of a critical number is a number C in the domain of f such that f prime of C is equal to 0 or f prime of C is undefined. And to be a critical number, C has to be in the domain of f.
ST is so that.
Such that. And the relative extrema of a function can only occur at a critical number, but not every critical number will represent a relative extremum. Okay, and my point with that is, if I came back up here, and let's say I extended this graph, and I want you to see where I extended it. So like, let's say that I made this kind of come down like so. Do you see how there would be a horizontal tangent line such that f prime of B would be equal to 0? But is f of B a relative max or min?
No, it's just in the middle.
No. There's just it ends up corresponding to something else that we'll be identifying, but it's not a relative max or min. So B, we can say B is a critical number that is not a relative max or min. So if we go back to, or first of all, let me pause for a second. Any questions on the relative extrema? So relative extrema have to occur on an open interval, and if relative extrema are going to occur, they're going to occur wherever the derivative is equal to 0 or undefined. So horizontal tangent line or like a sharp corner. So I want you to take a moment and look back at the graphs that you sketched on that first page. And for the functions that were continuous on a closed interval, where did the absolute extrema always occur? So looking back at those 4 graphs where the function was continuous on a closed interval, where did the absolute extrema always occur?
At a horizontal asymptote.
Well, not necessarily for
Not horizontal asymptote. I think you mean a horizontal tangent line.
Yeah.
So like for 2 sine of x, horizontal tangent line. Yeah. But what about
endpoints.
or I don't have an example of a sharp corner. But like, what if we thought about like absolute value of x on, let's say, the interval from -3 to 1, right? Wouldn't 0, 0 then be the location of the absolute minimum, that sharp corner? So, for a function that is continuous on a closed interval, so extreme value theorem applies, then we can say that the absolute extrema always occur either at the end point of a closed interval or at, what do we call those values where the derivative is either equal to 0 or undefined?
Relative extrema.
Yeah.
Oh,
A critical number, at a critical number. On an open interval. Or on the open interval. From A to B. And I also want to specify, like we mentioned critical numbers, if you're considering x comma y, we could call that a critical point. Would be where f prime equals 0 or f prime is undefined. Or I should call that C, here, I'll call that C comma f of C. So where f prime of C would be 0 or f prime of C would be undefined.
And then the critical number is just C.
The critical number is just C, exactly. Mm-hmm.
I'm a little bit confused. I thought that the relative extrema is always going to occur when f prime of c is 0 or undefined.
It is. For absolute extrema.
Yeah.
And in the case where extreme value theorem would be valid, like we're continuous function on a closed interval, where you know an absolute maximum and an absolute minimum both exist, the absolute max and min are going to either occur at an endpoint of the closed interval or at a critical value or critical number. I know, this is a lot. There's a lot of vocabulary here too, and needing to understand what the vocabulary means to understand like what is being asked. So to summarize, we have talked about the difference between global extrema, so that means like the very largest function value or the very smallest function value, versus local extrema, which is it's a high point and a low point, or a low point. Like it's, if there's an interval, like if you zoom in on the graph where that value looks like it's a high value, but it's not necessarily the overall highest value of the function. Or for a minimum, right? Like you zoom in on the graph and you're like, it looks like a low point of the graph, but it's not necessarily the very smallest or lowest point on the graph. Now, in the case that extreme value theorem applies, okay, so this would be for when extreme value theorem applies. So here, extreme value theorem, check, okay. These are the guidelines. So remember, extreme value theorem is an existence theorem. These are the guidelines that you can use to identify what the extreme values are on that closed interval, okay? This is also known as, in the College Board, not our textbook, but the College Board refers to this as the candidate's test. And you'll hear me refer to this as the candidate's test. And that's because you know there is an absolute max or min because the function is continuous on a closed interval. So then you're considering all the potential candidates, which would be the endpoints of the interval, as well as any critical numbers on the interval. And then you're going to test out, well, which one gives me the largest function value, which one gives me the smallest function value. Are we following this? Okay. So let's start with a polynomial, okay? So we want to, without graphing, like so far we've just been reading graphs to identify the extrema. So we are going to take this function, identify the absolute, maximum, and minimum. First of all, we know we can go through the candidate's test because f of x is what type of function? I think I already said it.
Continuous numbers.
Right, and you know it's continuous because f of x is what type of function? Polynomial. It's understood amongst us, polynomials are smooth continuous curves. So if you were to take just one interval of this function's implicit domain, like we're just taking the closed interval from -1 to 2, you know that this function would be continuous. Therefore, by extreme value theorem, you know that there will exist an absolute maximum and an absolute minimum, and we can identify what those values are using the candidate's test. Okay, so we know that -1 and 2 will be potential candidates. We need to see if there's any critical numbers on the interval from -1 to 2 for this function, which means we need to find, here we're actually getting into some calculus, right? We need to find the derivative. So let's find f prime. Okay, power rule. 15x to the 4th, what is that? Minus 28x cubed. Now, will f prime ever be undefined? No, because the derivative of a polynomial is a polynomial, right? So same thing goes, like we know this is a smooth continuous curve. So now we can just think about setting f prime equal to 0. And now we can factor. So I can factor out an x cubed. So we would get, as solutions to this equation, we would get x equals to 0, or, I'm just going to separate with a comma, or we would get x equals to 28 over 15. These are the critical numbers. Which come from f prime being set equal to 0. Here's how you set up the candidates test. You make a table where X, so all the candidates will be in the left column and the function values will be in the right column, because we're trying to figure out, well, which candidate gives me the largest function value, which candidate gives me the smallest function value. Here, I'll move it over here so I have more room. Okay, so again, my candidates, I will have -1 and 2. I will also have 0, because 0 is on the interval from -1 to 2. Is 28/15 on the interval from -1 to 2? Yeah. Okay. So f of -1, now it's just plugging in. F of -1, that ends up being -3 minus 7, so -10. And I'm plugging into the original function because I want to see what the function values are. F of 0 would be 0. F of 28/15, lovely. So that's plugging in 3 times 28/15 to the 5th power minus 7 times 28/15 to the 4th power. Sorry guys, I can't do that in my head. If you put it into your calculator, I believe it ends up being -16.998. And then f of 2 ends up being equal to -16. So, what's the absolute minimum? Yeah, here's our absolute minimum. And then the absolute maximum is 0? If you were asked for the location, you could describe the ordered pair, but if you're just being asked to find the extrema, that's find the absolute maximum and find the absolute minimum. It just refers to the function values. And if we were to go over to Desmos, oh, how do I do the,
It's a curly bracket.
and then I can I type in the inequality?
Yeah.
So -3 to 4. There we go. No, that didn't work. Why didn't that work? Do I not type the comma? No. I didn't like that. Did I do it wrong, you guys? That didn't work. Does it do interval?
It works when you don't have the white equals.
Does,
I know it's still working. The drill practice.
okay. With the inequality, typing it as an inequality.
Yeah.
All right, let's give it one more try. -3. Did I type it in wrong?
I mean, it's.
-7x. No.
Yeah, it is. It's just too big.
But that doesn't make sense.
The interval is -1 to 2.
Oh! Why am I typing -3 to 4, you guys? Oh, because the next one is. Okay. Okay, here we go. Hey, look! We did it! Yay! The minimum and the maximum. That's all recorded on video. That's fine. Okay. We did it though. That's what matters, right? We actually found the correct ones. Okay. So let's go ahead and find the extrema for this next function. Here's the thing, you guys. Do you know, you're like, oh, chain rule. Do you know what the derivative of the absolute value is?
X over.
Jumpman?
It is Jumpman. That's good that you guys remember that. But then there's also a little bit of chain rule in here. So you always could think about rewriting this as the square root of x squared minus 4 squared, like that. I think you guys end up being right, though. You do. X over absolute value of x. So then if I was thinking about chain rule here, I'm like, okay, f prime is equal to derivative of the outside. Leave the inside alone times the derivative of the inside, which also requires chain rule. Okay, so then this 2 can cancel with one of these 2's. How about that 2? You guys are right, because that'll be 2x times x squared minus 4 over, you can write that as absolute value of x squared minus 4. Or you could go through the step of writing that as the square root of x squared minus 4 squared. Okay, so f prime. First of all, f continuous, closed interval, okay? You guys know what the graph of this would look like, right? Like if you think about x squared minus 4, that parabola, x-intercepts at -2 and 2, but then taking the absolute value, it just reflects everything, all the negative points, like the points that have negative y values over the x-axis. So in order to identify critical values, we do need to think about where f prime would be equal to 0, as well as where f prime would be undefined. So for equal to 0, can't I just think about setting the numerator equal to 0? Do we see that?
Yeah.
So we could say 0 and then plus or minus 2. And then for f prime being undefined, we could think about setting the denominator equal to 0. Oops. Which we would get x equals 2 plus or minus 2. So actually, plus or minus 2 would correspond to f prime being undefined. Which means that our critical numbers are going to be, and I want to check that they're in the interval, will be 0, -2, and +2. All of those are on the interval from -3 to 4. So now we're set to do candidates test. So making my table, and people do struggle with like knowing what to put in the table. X is the left column. It's all the candidates, right? Which would be -3, so endpoints, as well as critical numbers. And then the right column is going to be the function values.
Why don't we put like -1 and 1?
Our -1 and 1 critical values, critical numbers.
Oh, right. Wait, but then why did we put -3 and 4 then?
Those are the endpoints.
They're
so
endpoints.
yeah.
Thank you. Okay, so plugging in those values to your original function. F of -3, so that would be absolute value of 9 minus 4, which would be 5. F of -2 would be 0. F of 0 would be 4. F of 2 would also be 0, and F of 4 would be 12. Okay. So then identifying, well, what's the smallest value? What would our absolute minimum value be? 0. And it occurs at 2 different points. That's okay. The minimum value is 0. It just occurs in 2 different locations. And then the absolute maximum will be 12. I think we're going to have time to do one more together. So I'm going to skip this next one for now because I think you guys can do it on your own. Let's get a little triggy.
Oh.
Yeah, okay. Sine of 2x, 2 cosine x, both continuous functions. So when they're added together, guess what? They're still continuous. On the interval from 0 to 2 pi. So we can go straight to finding f prime. Extreme value theorem applies, so we'll go straight to finding f prime. Now, if you wanted to, you technically could rewrite sine of 2x as 2 sine cosine and use a little product rule.
I'm good.
So many of you guys on the test, and I mentioned this, that a lot of people all of a sudden, when they don't necessarily have to, start writing down like they're approaching differentiating from an implicit differentiation perspective. So many of you this year. So many. I was like, wow, I haven't seen this many before. Which is fine. It's fine. It's just not necessary. Okay, so derivative of sine of 2x. So derivative of the outside would be cosine. Leave the inside alone, times the derivative of the inside is times 2. And then derivative of cosine is negative sine, so minus 2 sine x. And then we can think about just setting this equal to 0. Now, here's where all of your hard work solving trig equations last year is coming into play. How would we go about, what do we need to do in order to solve something like this? Let's assume it's not a graphing calculator active question. Tony?
Trig identities.
Trig identities. Which one do we want to use?
Cosine, cosine, sine, sine.
Cosine, cosine, sine, sine. Would that help? I want to have it all in terms of, yeah, so use the 1 minus 2 sine squared. I'm going to factor the 2 out first. Is that what you're saying?
Yeah.
Factor the 2 out? Yeah, let's throw that 2 out. We don't need it. And then I would probably use, since we have sine there, I would use, so going from cosine squared minus sine squared, because Tony's right, cosine, cosine, pause, sine, sine, right? Cosine squared minus sine squared. Replace that cosine squared, are we following this? Replace that cosine squared with 1 minus sine squared. Let me write this down. Yes, you have to know your trig identities, guys. Right? Cosine squared minus sine squared. Because x plus x, cosine, cosine, pause for the sign change, sine, sine. And then we can replace cosine squared with, thinking Pythagorean identity, 1 minus sine squared. And that gets us to 1 minus 2 sine squared for cosine 2x.
Do not have this. We memorized that before.
Remember when I was like, hey, you need to know these, you should memorize them.
Uh-oh.
I remember.
And some people have just been like, I hope she wasn't serious when she said that. Okay, so this will end up turning into 1, right? This will be 1 minus 2 sine squared minus sine. Hey, we have like a quadratic like trig equation.
I heard this kind of same. Oh, isn't it +1? Oh wait, no.
Is it?
No wait.
No, you're right. You're right. But I'm going to factor out the negative, and we can divide out the negative, right? So it's 2 sine squared plus sine minus 1. And then this factors 2 sine, right, to get the 2 sine squared. That'll be plus 1 over here, minus 1 over here. So we would have 2 equations from here. Sine of x is equal to positive 1/2, or sine of x is equal to negative 1. Both of these correspond to f prime being 0. And we only need to solve on the interval from 0 to 2 pi. So where is sine equal to positive 1/2 on the interval from 0 to 2 pi?
Pardon the interruption. We have some changes for lunch with the rain. If you guys can please remember to, all teachers can open up their classrooms so students can have lunch in there.
Great,
Also for the Math Honor Society luncheon, it has now been moved to room 17. Thank you.
17 pizza.
Oh, I forgot about that.
What?
over 6.
It is pi over 6.
And 5 pi over 6.
And 5 pi over 6. And then for sine equal to -1 would be 3 pi over 2. So you guys, these end up being our critical numbers, which then we can pop those puppies into our candidates test, into our table. So 0.
No, but like for a class period.
That's not a class period, it's a line, it's another lunch.
I know.
There's certain Mr. Mark's range on. So great. Have you heard it, Tony?
Yes.
Oh, yeah.
So he was doing a CITN and then just spontaneously.
Okay, plugging into the original function. So sine of 0 is 0. 2 sine of 0 would, or sorry, 2 cosine of 0 would just be 2. Okay, f of pi over 6. Okay, that'll be sine of pi over 3, which is root 3 over 2. Plus cosine of pi over 6 is root 3 over 2, so it would be plus root 3, or I want to leave it as 2 root 3 over 2 because that'll be helpful, right? 3 root 3, that's 3 root 3 over 2, and then f of 5 pi over 6. Sine of 5 pi over 3 would be negative root 3 over 2. And then cosine of 5 pi over 6 would be negative root 3 over 2, so minus 2 root 3 over 2 will be negative 3 root 3 over 2. And then f of 3 pi over 2. Sine of 3 pi is 0. Cosine of 3 pi over 2 is 0. So just 0. And then f of 2 pi. Sine of 4 pi is 0. Cosine of 2 pi is 1, so 2. Okay. Now, in case you were curious, this ends up being approximately 2.598, and this is approximately negative 2.598. So, absolute maximum, and I'm circling the whole thing because the whole thing is a representation. Each of those f of pi over 6, right, represents the function value. That would be the absolute maximum. And then f of 5 pi over 6 would be the absolute minimum. I think that's good. I think you guys have enough to do the homework, and I'm going to save the ones that we didn't get to as like a little warm-up for next time that we can do together. It'll be great.
I'm excited about the pizza.
Yeah, you guys, all of you are, oh, let me stop.